Thank you everyone for coming to this presentation. I'm going to talk about partial weight exchange in federated learning. This is work done with the whole FL for Health team, and this is a follow-up to a previous presentation that I also gave on this topic. So I'm going to briefly introduce you or remind you of federated learning. So it's a technique where distributed clients collaboratively train a model without sharing their private data. So the idea is that your data is distributed across different parties called clients, and you want to train a model using all of the data, but without collecting the data into one place for privacy concerns, for example. And the way you do this is by introducing another party called the server, and clients only send model parameters to the server after they train the model on their own local data. So here are the basic steps. So the global model is first initialized on the server side. The server then sends the global model parameters to the client, who then perform local training. And then the local model are sent to the server, then the server aggregates the models. And we just repeat this process several rounds. So the most straightforward algorithm is called federated averaging, which basically means that aggregating in step 5 is weighted averaging. So there are several challenges in federated learning. So for example, the heterogeneous client data distributions can affect model performance or convergence. And there's also the issue of high communication costs between clients and server and privacy and so on. But for this presentation, the approach that I'm going to introduce is going to focus on the first two challenges. Okay, so now let me tell you a bit more about the partial weight exchange algorithms. So the idea behind that is also very simple. So by default, federated averaging exchanges the entire model between clients and the server. This might be undesirable if your model size is very large because the communication cost can be very large. And the solution to this is also very simple. You just exchange certain parts of the model instead of the entire model. So here are the steps that I showed you earlier about federated learning. So the modification you would make is basically in step 4, instead of exchanging the entire model, you only send certain parts of the model. And then the server is responsible for assembling the parts and then aggregating the models. Okay, so any such approach has to consider several questions. The first is, what exactly do we exchange? Like, which parts of the model do we exchange? And how do we select which ways to exchange, and also how much to exchange? So I'm going to go into each of these questions as I explain the algorithm. So in terms of what do we exchange, I'm going to talk about two options. The first is to exchange entire layers. So here I am assuming that the model held by each client is a neural network consisting of several layers, where each one is parameterized by a weight matrix. So this approach is inspired by Rousseau et al. In this paper called Training Mixed Domain Translation Models via Federated Learning. And I'm going to call this model dynamic layer exchange from now on. So basically each layer has a weight matrix. The idea is that we only exchange the entire layer. So basically all the weights within the same layer are either all exchanged or not all exchanged. And we can exchange, for example, W2 and W3 and keep W1 at each client's location. And the second approach is to allow for exchanging arbitrary sets of weights. So let's say I zoom into this weight matrix, for example. The distribution of the parameter values can look like this. So this approach allows you to exchange any subset of the weights within the weight matrix. So you're no longer constrained by having to exchange all the parameters within a certain matrix. In this case, we also need to exchange extra information to help the server to aggregate. And I'm going to call this method sparse tensor exchange. And the second question is, how do we select which weights to exchange? Intuitively, of course, we want to select the weights that are important for model performance. So in this case, we drew inspiration from the sparsity literature, and I'm going to consider two selection mechanisms. The first is to select weights that have the largest magnitude after local training. The idea is like if you're far from 0 value, that means like the parameters are important, and vice versa. The second approach is to select weights that change the most in magnitude after local training. The idea is that they might capture the most information that's relevant to the task at hand. And in the case of exchanging entire layers, we also have to normalize by the number of parameters within certain layers so as to not bias towards layers that have more parameters. Okay, so the third question, how much to exchange? We just empirically experiment, try a bunch of different exchange rates for sparsity levels. Okay, so I'm happy to get into the details afterwards if anyone has any questions. But let me first show you some experimental results of these algorithms on health data. So in this case, I'm going to consider two tasks. The first is called FedIXI, it's a segmentation task on 3D brain MRI images. The second one, called FedISIC 2019, is a classification on dermoscopy images where the classes are highly unbalanced. So here are the training details. So for both tasks, every client trains their local model for 100 steps within each federated learning rounds. And we've used the AdamW optimizer and performed a hyperparameter sweep to determine the best learning rate. And I want to point out that for FedISIC 2019, it's important that we don't exchange any batch normalization layer. And I'll talk a bit more about this later. This turns out to be crucial for learning. And in terms of the evaluation approach, every client has a validation set as well as a test set. So after local training and server-side aggregation, every client evaluates its model on the validation set, and we just checkpoint the model that has the best validation performance throughout training. And after the entire training process finishes, every client has its own model, which is then evaluated on the local test set. And we just report the average test performance across clients. Okay, so here are some more details of the segmentation task. We have 3 clients, and the number of data points is as follows, distributed across clients. The model architecture considered here is a 3D UNet with, roughly speaking, about 1 million trainable parameters. We'll just measure the dice coefficient, which basically is a similarity measure between the actual target and your model prediction. And here are the some results. So here the y-axis is the dice coefficient, which basically means test performance. The x-axis are the exchange percentages, where it indicates the percentage of layers that are exchanged. Because, well, first I'm showing the approach where you're exchanging entire layers that have the largest magnitude change. So for example, 0.4, if you look at this bar, it corresponds to the case where 40% of the layers are exchanged. I want to bring your attention to the first and the last bar. So here 0.0 means that nothing is exchanged at all. So basically each client just trains its local model on the local data. This is the baseline that we use for comparison. And the last bar, where it's 1.0, basically means I'm exchanging the entire model. So this corresponds to federated averaging. So the interesting thing you can see on this diagram is that as we increase the percentages of layers exchanged, you see this dip in performance first, but then it increases later. The takeaway here is that you can actually get away with only exchanging very few layers and still getting pretty good performance. So basically, you can reduce the communication costs without compromising performance too much. And here are the performance for sparse tensor exchange. So here, similar to before, the sparsity level indicates the percentages of the weights that are exchanged, except now you are no longer restrained to exchanging entire layers. And the takeaway here is again that, well, it's actually different. As you increase sparsity levels, in general, the performance increases. But I want to bring your attention again to the last few bars where you can see exchanging the entire model actually is slightly worse than exchanging, let's say, 80% or 90% of the weights. The improvement here is pretty small, but it's more for the other task. And the second task here is an image classification task of FedISIC 2019. We have six clients here. And the challenge that this data set presents is that the data points across clients is highly unbalanced. Like one has 400 data points, but the other one has 12,000. So in this case, we're using an efficient net with about 4 million trainable parameters. And here are the results for exchanging entire layers. And the takeaways, so the numbers doesn't look very high. None of them reaches 70%, but these are actually pretty good. We also experimented with several other federated learning approaches, and here, like 66% is actually pretty good. The takeaway here is, again, I want to bring your attention to the last few bars, where exchanging the entire model actually produces worse performance than only exchanging certain parts of it. And here are the results for exchanging arbitrary set of weights instead of layers. And you can see the increase, the performance benefit provided by only exchanging a partial exchange is actually more drastic here as well. Okay, so I want to talk about a few points that I want to discuss about these experiments. The first is that it's very important to not exchange batch normalization layers for Fed-ISAC 2019. But I think in general, it's also an important practice because especially in the case where your data is very heterogeneous across different clients, it doesn't really make sense to, where your batch normalization layer keep tracks of some statistics of your local data, it doesn't really make sense to aggregate them if your data is very distinct across clients. But I don't think this is a practice that's widely adopted in FL as of now, although some researchers have pointed this out in their papers. The second is that apart from reducing communication costs, partial weight exchange actually can be viewed as a method for personalized federated learning because each client ends up having its own model that's sort of adapted to the local data distribution. And this might explain why in some cases, not exchanging the entire model actually has performance benefits as well. The third point is like in reality, the communication costs saved by our approach is actually not as much as would be indicated by the sparsity level. So for example, if my sparsity level is 40%, that does not mean that the communication cost is 40% of that of the full exchange rate, because I need to send extra information to the server in order to help aggregation. And the last point is like, it's a caveat, even though there are some performance benefits that observed within these two tasks, there's actually no theoretical guarantee for convergence for partial weight exchange, as opposed to some of the other full exchange methods. Yeah, and with that, that's the end of the presentation.
Questions?
Yep.
So I think you mentioned that, for example, in all the instances of training the model, you use the same number of steps, maybe 100 steps. So similar to that, are all the hyperparameters of the training process same as well, maybe learning rate, or do they different from client to client? Because maybe one client does not see a convergence using a learning rate of 0.1, but the other client might see a convergence with a learning rate of 0.1. So
so in practice, we actually did a hyperparameter sweep on all of the clients. So every client would try out a bunch of different learning rates. And in the end, because this is a personalized federated learning approach, meaning that every client would end up with its own best model, right? So we actually tried that. It's just I didn't write it in the presentation.
Thank you.
I just wanted to ask a question that I hope would benefit the audience here, which is, let's suppose there's a hospital or a collection that wants to train a model. So what kind of exchange strategy would you recommend for them to get the best performance out of your research?
The best takeaway, the best advice I can give is don't change batch normalization layers.
All right, well, I'll remember that, right?
Yeah, I mean, I say that like half jokingly, but half serious. It's actually quite important. Like for example, these numbers here, you can see we can get close to 70%. But if I exchange batch normalization layers, it's 12%. So,
thank you.
I feel like you talked this a little bit, but for my benefit, can you explain what's the theoretical reason for why you would get better results on a partial exchange versus exchanging full models?
So there are actually no like theoretical guarantees for that. And this is why in the last point I said we don't even get theoretical, like there's not even theoretical guarantee for convergence, in the sense that it's conceivable that you wouldn't even get something that converges to the best loss. But the point is that we tried partial weight exchange because the issue with communication costs can conceivably be very important when, especially when the model size is getting larger and larger nowadays. As for why, in this case, we saw better performance in partial weight exchange than full exchange, it might be the case that we only like the weights that are specific to the local data is kept rather, but in the case with full exchange, they would be aggregated. So essentially, partial weight exchange might allow each client to end up having a model that's more well adapted to its local data. So that's the intuition behind that, but yeah, I don't think I can give you a proof on